Okay, so this is lecture, I guess, number 14 here that you've heard from me, not counting our guest lectures and project pitches and so forth. Yes, or Tuesday rather, we introduced optimization, kind of the broad field of optimization, which is very broad and very deep and contains far too much for us to really cover in any detail in this class. But then we talked about kind of a specific subset of optimization problems for which we can get reasonably good solutions in a reasonably efficient amount of time. And so we talked about basically sort of zooming in on that stuff, which is called convex optimization. And so we will talk today a little bit more about kind of what that term convex means. You may have heard it in a calculus class or something as kind of having to do with the curvature of a function, something that's concave up or concave down. Concave up basically means convex, and concave down means, I guess we would call it concave in this class. But so today we will talk about sort of what does convexity mean, both for a set, and we'll talk about sort of the geometric interpretation there and also for a function. And then we'll give some examples of convex sets and convex functions. And those are useful basically for specifying optimization problems, which really is minimizing a convex function over a convex set. And then, so spring break, and then we'll come back in about 2 weeks, and we will talk about algorithms for convex optimization and software for solving convex optimization problems. And once we have these 3 lectures under our belt, again, we won't be experts, but we'll be kind of know enough to be dangerous. And so then we can put our newfound skills to work on some DER problems. And so this lecture, lecture 16, will basically just talk about what are the different things we might want to do in a DER optimization problem? What are the different objectives that we might have? And then we'll go into some specific examples, looking at a battery. This lecture on regression will be about kind of model fitting and predicting things. So predicting energy use, predicting, for example, the water draw usage from a water heater, something like that. Talk a little bit at the end about optimization under uncertainty. So everything above this in the optimization unit kind of assumes that we have perfect information. So we know exactly all the models of all the equipment in our system. We know exactly what will happen in the future with energy prices, for example. But what happens if some of those things those assumptions are not very good? So for example, if we're working with a photovoltaic solar array, we might really care about how much energy we're going to produce at a certain time in the afternoon. And as you guys all know, weather forecasts can be pretty good. They've kind of gotten better over the last decade or so, but they're still leave a lot to desired. It's still a really hard problem. So of course, solar photovoltaic output is dependent on sunlight and cloud cover and these things, which are challenging to predict. So at that point, yeah, you guys will know how to model and understand physically DERs. You'll know a fair amount about energy systems and the economics and policy of energy, and you'll know how to do stuff with DER optimization. So I'm looking forward to seeing what you guys do with that knowledge in your class projects. Right, so today's lecture about convex sets and functions. Here I'm drawing on materials. There's a textbook called Convex Optimization by Stephen Boyd, and I think his co-author is named Vandenberg, if I remember correctly, at Stanford and Berkeley, respectively. But Stephen Boyd on his website, and if you click this, you can follow the link, has lots of materials, both videos and slides and a textbook. They're all freely available there. So if you want more detail on the stuff that we're talking about today, you can find it there. So today's outline, we'll start with talking about convex sets. We will move on to talking about convex functions. The definitions of convexity are pretty closely related between the two, but have some distinctions. We'll talk about what are called composition rules. So if you have a function of a function, how do you know if, depending on the properties of the inner and the outer function, how do you know if the composition of those two is convex or an increasing function, a decreasing function, something like that. And then we'll give some examples. And this basically is a sampling of kind of the library of convex functions that are used in the software, which we will eventually put to use for solving DER problems, which is called either CVX, if you use it in MATLAB, or CVXPy in Python. Okay, so to understand convexity, I guess I'll just preview this. A set, which you can think of as a shape, a geometric region, is convex if it, for any 2 points within the set, you can draw a line segment between them, and that line segment falls entirely within the set. So I'll show kind of a schematic, a little illustration of what that means. But first, let's talk about mathematically how we can describe line segments. And so that's kind of easy if we're looking at sort of a plane, but what about in higher dimensions? So suppose that we're in an n-dimensional space and could be 3 or it could be a billion. And we have 2 points, x and y, which are in that same space. So this set here, the set of all combinations, theta x plus 1 minus theta y, parameterized by this thing theta, where theta is a number between 0 and 1, the set of everything that you can get. So this would be a scalar times a vector. So this thing here is an n-dimensional vector. This is another scalar times a vector. So everything on the sort of left-hand side here is an n-dimensional vector. So this is the set of all vectors that you can get as basically a mixture of the 2 points x and y. So if theta is 0.2, that mixture would be 20% x and 80% y, for example. So this is called a convex combination or a mixture model. So this set here describes the line segment between x and y. And so this is what this looks like geometrically with a point x, a point y, and of course the line segment is in between here. So here I'm showing two points, a point y over here and a point x over here. And then this is the origin, so you could think of this as the 0 vector. And then this is all just review for you guys, but if this is y and if this is x, we can view those either as vectors or at points. Let's think about them as vectors. Then this thing here that starts at y, it has the tail of the vector at y and the tip over at x. This thing here is the vector x minus y. And you can kind of see that vector addition basically goes, you take one vector, you attach the tail of the next vector to it, and you kind of go along there. So if we take y plus this thing, x minus y, well, that must be equal to the vector x. All right, so with that in mind, we can get a geometric illustration of this line segment thing. Okay, so here again, we have the same points x and y. We have the origin over here, and this is the vector that just points to y. So this you can think of as a really stupid convex combination, but nonetheless a convex combination of x and y, where we have 0% weighting on x and 100% on y. And then as we increase the weight on x, we begin to move along the line segment between x and y. So here we're showing 10% x and 90% y. Here 50-50 mixture. Here a 90-10 mixture where 90% of the weight is on x. And then, of course, if we have theta equal to 1, we get all the way to the vector x. So that's just illustrating geometrically this formula for line segments in R. Okay, so then we get to a definition of a convex set. So pick some set C. This symbol here means a subset of. So C, a subset of the n-dimensional space here, is convex if for any 2 points in the set. So pick any x and any y anywhere in the set. And pick any number theta between 0 and 1. Then this thing here, the convex combination of x and y weighted by theta, is also a member of the same set C. So this is kind of the mathematical or algebraic definition of convexity. And here's what that looks like geometrically. So again, the intuition here is that C contains the line segment that connects any 2 points, call it x, call it y, within the set. So this is a convex set. You can kind of convince yourself that whatever 2 points you pick, the line that you draw between those points would fall entirely in the shaded region here. And then this kidney-shaped thing over here is an example of a non-convex set. So there are many x and y pairs, in fact, infinitely many that you can pick and draw a line segment between them, and the line lies entirely in the set. So you could pick, a couple over here, and that would be fine. But the definition of convexity requires that that is true for all points x and y in the set. So here's a counterexample. You can pick an x over here and a y over here, draw the line between them, and that line does not lie entirely inside the shaded region. There are parts of it that are outside here. Okay. And so we get that this is not a convex set. Okay. All right, so that's an Rn. Let's think of some simple examples in R, which is just the real line, the one-dimensional space of real numbers. So one example of a non-convex set would be 2 points, the points 0 and 1, for example. So even though this is a super simple set, if we drew a line between 0 and 1, there would be lots of stuff on that line that's neither at the point 0 nor at the point 1. So non-convex. Another example would be say the set of all real numbers for which the absolute value is greater than 1. So this would be all the things to the right on the real line of 1, plus all the things to the left of -1 on the real line. And so again, there are lots of things. You could take -1 and -2, draw a line segment between those, and you're entirely within the orange set here. But if you take, for example, -1 and 1, those are both in the set. But if you draw a line between them, none of that line lies basically inside the set. So we get that this thing here is non-convex. All right, so that's very simple examples. Let's look at some more complex examples in higher dimensional spaces. So kind of the generalization of a line or a plane to higher dimensions is what we call a hyperplane. So hyperplane is defined as the set of all x within the space Rn. So this is n-dimensional vectors x, such that if we take a vector A and take the inner product of A and x, this is the dot product from your vector calculus class, and that's equal to some constant b. So any vector A non-zero vector A and any constant b define a hyperplane in Rn. And then we could do an equivalent representation, which is sometimes a little bit easier geometrically, which rather than having the constant b here, we replace it basically with a point x tilde, such that the vector A transpose x tilde, this inner product or dot product here, is equal to the constant b that shows up here. So you can see if A transpose x tilde is equal to b, put that in on the right-hand side, subtract it off and factor out the A, and we get that A transpose x minus x tilde is equal to 0. We get that as sort of our definition of the set. So here is what that looks like. So here n is equal to 2, but you can imagine this in Rn as well. So a hyperplane in R2 is just a line. And so here is the line, the set of all x1, x2, or all x1, x2 pairs, such that A transpose x minus x tilde is equal to 0. So here's a point x tilde, here's the vector A, and of course, when the dot product between two vectors is 0, you remember from vector calculus that means that the vectors are orthogonal, perpendicular. So basically, this is the set of all things that are perpendicular to A. And so here is one x that lies in the set here, the hyperplane. So let's see, the vector x minus x tilde would go from x tilde to x. And so here that vector is clearly perpendicular to the vector A, the normal vector A. And here's another example. The vector x minus x tilde would point like this, again, orthogonal to A, right? And in higher dimensions, you would have the same thing, just you'd have vectors pointing in more than 2 dimensions or 2 directions. Okay, so that is a hyperplane. A half space is something that's closely related to a hyperplane. So any hyperplane you can think of as basically cutting the space Rn in half. And so a half space is sort of everything that's on one side of that hyperplane. So here, rather than having A transpose X equal to B, which would define sort of the surface, the plane, we have less than or equal to B, and that defines the hyperplane. And similarly, we can write it with the sort of X tilde rather than B as the parameter. So this is the half space. So here, this would be the hyperplane. And then again, everything sort of below that hyperplane is our half space. And so this isn't meant to be a rectangle. This is meant to kind of go on in all directions, if that makes sense. Okay, so hyperplanes and half spaces we care about because they are convex sets. In fact, really important sort of atomic convex sets that we can combine in interesting ways to build new and richer sort of convex sets. So here is just a quick illustration of the convexity of a hyperplane. So here, basically, we want to verify the definition. So we want to take any 2 points that are in the hyperplane, so call them x and y. So there would be 2 points that satisfy ax less than or equal to b and ay less than or equal to b. And then pick any number theta. So we'll leave that as a variable and then show that this is going to hold for any theta. Okay, so now we want to basically say that any convex combination of these things, any theta x plus 1 minus theta y, is also in the hyperplane. Meaning if we take A transpose, multiply it by that convex combination, we want to be able to show that that resulting vector is going to be no larger than the right-hand side b. So we do this, we distribute out the a to each of the terms here. The scalars, the theta and the 1 minus theta, we can kind of factor out of the dot products. And then we have a transpose x less than or equal to b. And then we're multiplying by a number theta, which is non-negative. It's it can't be any smaller than 0. And then again, over here, we have a transpose y. Well, that's less than or equal to b. And 1 minus theta is again non-negative. The biggest theta can be is 1. So 1 minus theta is always greater than 0. And so then we get that the stuff on the right-hand side here is no larger than theta b plus 1 minus theta b. And then the theta b's cancel, and we're left with just 1 times b. And so we've shown here that a times the convex combination is less than or equal to b, meaning the convex combination is in the set. And from that, we conclude that it's the half space is convex. And this whole thing, you can run the same argument with an equals sign here for the case where these are actually in the hyperplane, not in the half space. So we'd have equalities rather than inequalities. Okay, another important property of convex sets is that if you take any intersection of two convex sets, that the intersection is also convex. Okay, so suppose we have a bunch of sets, C1, C2, could be an infinite number of them, could be 12, could be a billion, could be infinity. And they're all subsets of Rn, so they contain n-dimensional vectors. And each of them we imagine is convex. So then let's take any 2 points that are in the intersection of all these convex sets. And here this cap thing here just means intersection. And over I here, this means the intersection over all of the different I vectors. So this means basically that for all I, x and y are both in the set Ci. Okay, then we know the Ci sets are convex. So we can pick any theta between 0 and 1, and we get that the convex combination of any x and y is also in that same set Ci. So because that is true, we get that the convex combination here is in fact in the intersection of all of the Ci's. So, all right. So so this is a fairly simple idea. I guess maybe I should have an illustration here geometrically, but you can imagine a Venn diagram sort of thing, where you have a couple of circles or oblong, but convex shapes. You take the intersection of the two of them. That's kind of like the intersection of the Venn diagram. And that thing in the middle also is convex. So a polyhedron is an important type of convex set, probably the most important for optimization purposes. So a polyhedron is basically the set of solutions to any finite number of linear equalities, so linear equations, plus linear inequalities. So basically any x in Rn that satisfies all of these inequalities. Another way of thinking about that is that it's in all of these half spaces, and that it also satisfies these equations, meaning that it is in all of the hyperplanes defined by the C and D objects here. And you can show this basically by writing this thing as an intersection of a bunch of hyperplanes from here and a bunch of half spaces up here. So by the intersection rule, we get that, hey, we have a bunch of convex sets, hyperplanes, and half spaces. And so therefore, the intersection of all those sets must also be convex. That tells us that polyhedra are convex. Okay, so here's an illustration of a polyhedron in R2 in the plane. So we have a bunch of half spaces, each defined by one of these normal vectors, AI. So that defines the hyperplane here. So AI transpose X less than or equal to some BI, and then everything below that is in that half space defined by the A1. And then we do the same thing for all of the other A's, and the intersection of all those half spaces. We cut away half of the plane each time we do it, and we get a polyhedron. Another word for a polyhedron is a polytope. Sometimes people call them that. Sometimes people say a bounded polyhedron, meaning one that doesn't go to infinity in any particular direction, is a polytope, but I think we use the terms interchangeably. Okay, so that's all I'm going to talk about with convex sets. There are many other types of convex sets. Ellipsoids are a common version, so kind of circular or oblong ellipse type shapes. And those come up in lots of applications as well. And then there are weirder, more esoteric convex sets that show up in high dimensional spaces. But for our purposes, we probably don't need those. Okay, so that's convex sets. Next, we will talk about convex functions. So there's one way to think of the definition of a convex function in terms of the stuff we've already learned about convex sets. To talk about that, first we need to talk about the domain of a function. So here we use a little bit strange notation. I think in a math class, you would say a function f maps from a set D, which is called the domain of the function, to whatever space R or something like that. But for our purposes, we just write f from Rn to R, which basically tells us it's more or less specifying the syntax of the function. It takes n-dimensional vectors in, and it produces, for example, scalars as an output. So then with this notation, we define the domain of f as just the set of all inputs to the function for which the function is well defined. So for a function from R to R, the logarithm, for example, we might say the log is only well defined for positive numbers. And so the domain would be the set of all x that are strictly positive, strictly greater than 0. Okay, so the epigraph of a function, so the graph of a function would be like the set of all xy pairs, where y is f of x, right? We all know about that. So the epigraph is basically the set that lies above the graph of the function. But there's a little wrinkle here, which is that it also has to be, the arguments to the function also have to be in the domain of the function. So here y is a scalar, x is an n-dimensional vector. And so here we're sort of stacking an additional scalar, like you can think of it as appending it to the bottom of a column vector. So x would have n entries, and entry n plus 1 would be y here, just a number. So y here has to be greater than or equal to the function value f of x. So that tells you y is above the graph. So here's an example of what that looks like with a very simple function, just x squared. But suppose that we restrict the domain of f such that we're only interested in arguments that are greater than 1. It's like just a weird example to illustrate the epigraph and the interplay between the epigraph and the domain of the function. Okay. So here, the solid black is illustrating kind of the well-defined function values. And then the dashed lines here are like sort of what the function value would be if we allowed it to be defined between -1 and 1. Okay. So then the epigraph here is just the set of all stuff that both for which x is in the domain of the function, so the blue shaded area here, and the stuff is above the graph. So we get these two kind of like wedge regions here. And anything that is in any of the orange area is in the epigraph of the function f. Zach, was that a question or just a?
So if y was less than x, it would be below.
Yeah, if instead of y greater than or equal to f of x, we had y less than or equal to f of x, then we would be cutting out all the stuff that's above. Oops, what did I do here? Above the function, and we would shade all the stuff that's basically below the function, all the stuff in this area. And there's probably a name for that, like the subgraph or something. But yes. For this case?
For if it was below.
For if it was below the function. Yeah, you could go down into the negatives. So yeah, you could go down below the x-axis.
Our value of x is negative in this case, we go positive, not just 0.
Yeah, so you could think of, right, so this doesn't, yes. So if we lowered this function down, if rather than x squared, we had like x squared minus 10, then most of this thing would be below the x-axis. And yeah, we would still go below the x-axis, so that counts as well. And actually this set here would go up basically to infinity. You could draw it as high as you want. I couldn't find an infinitely large slide to put it. Okay, so one way to think about convexity of functions is just to say a function is convex if the epigraph of the function is a convex set. Okay, so then we just appeal to all the definitions and examples and stuff that we just went through, and in theory, you're kind of done. but that doesn't build all that much intuition. So equivalently, we get that the domain of F must be a convex set. Okay. And so that actually is where we fail here. So x squared is a convex function. It's kind of a canonical convex function. It's just a bowl-shaped thing. But because we restrict the domain to this non-convex set, the set of x for which the absolute value is greater than 1, we get that the epigraph is in fact not convex, right? Even though x squared is a bowl-shaped thing. Okay, so we need the domain of the function to be a convex set. And then we need this property that for all x and y within the domain of x, and any theta between 0 and 1, if we take f of the convex combination of x and y, that has to be below the convex combination of the function values, f of x and f of y. And so geometrically, again, we get an interpretation here that if you pick the point x comma f of x, so this would be, I guess, a point in Rn plus 1 if x is an n-dimensional vector. And another point, y, f of y, in that same n plus 1 dimensional space. And then you draw the line segment between those two things. That line segment would always lie above the graph of the function. So let's look at what that means geometrically. So here we're looking at a simple function. I think this is like, I don't know, whatever, x minus 1 squared plus 1 or something like that. But black is the function. And then there's a point x down here, another point y down here, chosen more or less at random. And this is what's called the chord. So it's the line segment that connects the 2 points that are on the graph of the function. And so here we're looking at a point basically that's on this line. So the value of theta is 0.1. And then again, we can kind of march forward through progressively larger values of theta. Here's theta 0.5. Here's theta is equal to 0.9. And then for theta equal 1, we would be over here at the point x comma f of x. So this is just trying to show that the orange here, this is the thing that shows up on the right-hand side of this inequality. This is the orange, and then the blue thing on the graph is what shows up on the left-hand side of the inequality. So here I'm trying to show that the blue stuff for this convex function is always below the orange. Okay. A concave function. So f is concave if negative f is a convex function. So concave, rather than thinking of as kind of like a smile shaped or something, it's like a shaped. So here's f, and here is negative f. We can verify basically that negative f is a convex function, and then that tells us that f is a concave function. So anyway, if you understand convexity, that's sort of sufficient, right? Like up to a minus sign, you've understood concavity as well. The function is called affine if it can be written as, affine functions are an important example of convex actually and concave functions. And a function is affine if it can be written basically as ax plus b. So we're a little bit specific with language in this class to differentiate linear functions from affine functions. Y equals mx plus b is the classic equation for a line in sort of two-dimensional space. But here we would say that a line, mx plus b, is actually an affine function of x, not a linear function of x, unless b is equal to 0. Anyway, affine functions are necessarily convex. So we can show that basically by verifying the definition. So if we take the convex combination here, we want to show that that thing is no larger than the convex combination of the function values, f of x and f of y. So here we do that. We just apply the definition. Well, f of x, that's theta x plus b, or sorry, ax plus b. So we're just applying the definition of f here. Now we again just distribute the dot product. So a goes into x and it goes into y, and the scalars theta and 1 minus theta factor out. And we haven't touched the b at all over here. And now we can group terms. So we can group the theta terms here. So we've got an ax. And over here, we also have a minus theta ay. Oh, sorry, we keep the ay in here because I see what we're doing. We're basically splitting b into, you can write b as theta b plus 1 minus theta b. So the plus theta and minus theta would cancel there. And so then we can put some of B basically into this term and put the rest of B into this term. And so we can group it according to the theta and the minus theta here. And then we know that A transpose X plus B, well, that's just f of X. And A transpose Y plus B, that's just f of Y. And so we get actually equalities here, equations, not inequalities. And so this tells us that basically f here is a convex function, right? It's less than or equal to the right-hand side, but it's also a concave function, which would have a greater than or equal to sign here as well. So it's both convex and concave. And you can show that the converse is also true. So if you have any function that is both convex and concave, it ends up being an affine. Okay, so that's all I'm going to say about sort of the math of convex functions. We'll get into some examples of convex functions and some graphs and pictures of convex functions in a sec. But before we do that, I want to talk about composition rules for both convexity, concavity, and for monotonicity, so increasingness or decreasingness of a function. And this isn't just being done for math's sake. The reason for this is that we get basically the ability to start from some kind of simple atomic convex functions and build up actually quite complicated and interesting convex functions by applying our composition rules. And this is really the art or the craft of convex optimization, is to basically formulate your problem in such a way that it both captures the objectives and the constraints that you're really dealing with, but also obeys these rules of convexity so that you can apply a nice convex optimization solver. Okay, so before we get into composition rules for convex and concave functions, we need to talk about basically increasing and decreasing functions. So monotonicity here just means kind of, I don't know, monotone is like, either increasing consistently or decreasing consistently. So a function is non-decreasing if x, so this is for a scalar valued function. So we're going to only talk about scalar valued functions of scalars. So here x is just a number and y is just another number. So if the argument, the input to the function x is bigger than some other input y, then we get that the function value is also bigger than the function value. So if you graph a function, basically it's just going up or staying constant. And then we say a function is increasing or strictly increasing if these inequalities hold in a strict fashion. And then the opposite, as you imagine, is also true. So if you have a non-increasing function, that means that if you have a bigger value of the input to the function, you get a smaller or equal value of the output of the function. So here, non-decreasing functions, basically they preserve the direction of the inequality. And then non-increasing functions or decreasing functions switch the direction of the inequality. Okay, so if a function f is convex and non-decreasing, so here's an example of that. Convex, it's got kind of an upward curvature, and non-decreasing, meaning as we go from left to right on the x-axis, we're going up on the y-axis. So if f is convex and non-decreasing, then we take negative f. Well, we already know because f is convex that negative f is concave. And actually the negative sign here also changes the monotonicity property. So rather than being non-decreasing, it is non-increasing, meaning as we go from left to right, we go down on the y-axis. Yes?
It's like probably very basic considering the points that we talked about. But remember we said that you all line between 2 points on the set and not leave the set for the convex. Can't we draw 2 points on that line f of x and leave the set?
Yeah, so the question is about the definition of convexity. So we said for convex sets that if you pick any 2 points on the in the set and then draw a line segment between them, that line segment has to lie entirely in the set. So that's the definition for sets. For functions, basically we have that same thing, but it has to lie in the epigraph of the function, meaning the set of stuff that is above the function. So if we drew the epigraph here, it would be like a, I don't know, bowl, blue bowl with this curve on the bottom. And so even though the line segment that would connect 2 points is above the graph, it is in the epigraph. So we're all good. Yeah. But good question. Thank you. And I know this is a lot to throw at you guys quickly, so yeah, Zach. Yeah, so the orange function is concave. So if we drew the epigraph of the orange function, epigraph always means over, right? So we draw the epigraph, and it would be all the stuff that lies above this thing. So it would be kind of like a, I don't even know, what is a shape that like has a weird wiggle like that on the bottom and then extends above. I don't know. But anyway, so the epigraph would be the stuff up here. And then we could do the test that Grant just brought up. We could pick a couple of random points, say a point here and a point here, and we would draw the line segment between those points. And that would be not in the epigraph, right? Because it would be below the function. And so this would fail the test for convexity. But exactly, but that's okay because this orange thing is a concave function, not a convex function. So we could come up with an equivalent test for concavity, which would be, is the line segment in the set of stuff that is below the graph? And then we would be okay here. But yeah, these are important distinctions, so good questions. Okay. Another property that is useful is if you have a function f that is convex and non-decreasing, which by the way, this will show up, convex non-decreasing functions are basically functions that we can stick another convex function into, and then the composition of those functions remains convex. So if we have one of these convex and non-decreasing functions, it's sort of a nice function, and we take f of negative x rather than taking f of x. So basically we flip this thing, we mirror it over the y-axis. Then that function is again convex, which is nice. But now rather than being non-increasing, sorry, non-decreasing, meaning going up, now it is non-increasing, meaning going down. So we retain the curvature property, the convexity property, but we flip the monotonicity property, the increasing or decreasing property.
The additional convex function too.
So the nice one for our upcoming composition rule on a slide or two is the blue one. So we sort of like convex non-decreasing functions. So yeah. Yes, Tanya. Yeah, so the question is, could you have a function be non-decreasing but restricted only to some range? And yeah, absolutely. So like the function x squared for negative x is going down, right? So it's non-increasing. For positive x, it's going up, it's non-decreasing. And so if you restricted the function f, you said the domain of the function that I care about is only positive numbers. Then yeah, x squared would be a non-decreasing function. It would have these nice properties. And yet, yes, you do have to then restrict it if you want to use those sort of composition rules that are coming up again in a slide or two. Yeah, thanks. Okay, next slide. So there are sort of many special case composition rules, but this one basically gets you most of the rules that are useful in practice. Not all of them, but most of them. So we're going to do compositions of functions, and we're going to take these hi functions and compose them with this g function. So suppose we have functions h1 through hm. They each take in an n-dimensional vector and they return a scalar. And then we have m of those functions. And then suppose we have another function g, which takes an m-dimensional vector and produces a scalar. And then let's define our function, the one that we want to test basically for convexity. Let's define this function as the composition g of, this would be a vector h1 of x through hm of x. So the component, the first component that goes into the function g is just h1 of x, and so on down the line. Okay, then we get that f is convex, which is great, meaning we can plug it into a convex optimization solver and get, globally optimal results in polynomial time. Wonderful. If we have several conditions here. So if f, oh, I see. And g, we assume is convex. So the outer function here, we're assuming is a convex function. So then f, the composition g of the h's, is convex if h is affine. So if h has the form, each of the hi has the form A transpose x plus b. So if we take basically linear or affine equations, we stick them into a convex function, the composition is again convex. That's one possibility. Another possibility is that G is non-decreasing. So G is both convex and non-decreasing. And the functions H are convex. So in that case, we again get that the composition is a convex function. So a convex non-decreasing function of a convex function is convex. Okay. And then we have another case, which is G is non-increasing. Okay, so G is kind of going down along the x-axis. And HI is a concave function. So in any of those cases, we get that the function f is convex. And so I guess another way to remember this, it's a little bit less precise, but maybe more memorable. A convex function of an affine function is convex. So this one is very useful. A convex non-decreasing function of a convex function is again convex. This one also comes up all the time. This case doesn't come up quite as often in my experience, but again, can be useful. So a convex non-increasing function of a concave function is convex. Yes.
You have any way of depicting this graphically?
Can I, rather than saying a million confusing words and giving you numbers, depict this graphically? Maybe. I don't think I made any slides with pictures on them to illustrate this. It's more, in my experience, a little bit more of like an algorithmic check that you can do to convince yourself of convexity. It's a little bit harder to visualize. But that being said, I can think about it and come back with an example, maybe.
Non-increasing concave to plug a larger number in for the concave function forces it to be non-increasing.
So a good example of convex non-increasing for the last line here would be like 1 over x.
I think I see where you're getting at.
Yeah.
Like, kind of, like, it just curls it more versus like you put in the number that's higher.
Starts concave to force it to be. It gets smaller, but it's still
Decreasing, if it's non-increasing, it's starting down. Then you put concave.
Yeah, I mean, so you can imagine, so a concave function would be like negative x squared, for example, bowl-shaped function. So think of that. And then think of 1 over x as a non-increasing function. So a convex non-increasing function. So negative 1 over x, plug in 1 over x, plug in negative x squared to that. You get negative 1 over x squared. So what does that look like? Okay. I've confused myself. I should just draw pictures.
Graphically, just like you said, just plug in and get it. It's something we can also do with guys here.
Yeah, play around with it, right? Like pull up a graphing tool of your choice and plug in some functions and build some graphical intuition for that. I think that's a nice idea. Yeah. Okay. So the composition rule for concave functions more or less follows in sort of the same pattern as what we had for convex functions. So again, we're going to look at a composition G of H of X, but now we assume that the outer function G is concave, and we want to come up with conditions that tell us when a composition is a concave function. So you could get these rules basically by just putting minus signs on everything that showed up on the previous slide. But in case it's you need this for some reason, I don't know, sometimes it's valuable to have the rules just written down. So it all looks the same. F, we're testing for concavity, not convexity. So if we take a concave function of an affine function, we're good. We don't need to check anything else. We're guaranteed concavity. Similarly, if G is concave, non-decreasing, and H is concave, then we get that the composition is concave. And then again, if G is non-increasing and concave in each argument, then the result is and H is convex, then the result is again a concave function. And so you could write down more memorable kind of rules like this for concave as well. So interestingly, we can, when we get the rules for concave functions, we replace convex everywhere with concave. So we flip sort of the curvature property, but the monotonicity properties remain the same. So we still, in the second rule, we still have non-decreasing. And in the third rule, we still have non-increasing. All right, so those are the general rules. They're a little hard to visualize and a little sometimes challenging to apply in practice, although very useful. There are some simple special cases that come up all the time that cover, many of the applications that you probably will encounter. So one of them is if you have two convex functions and you just add them, that the result is again convex. Another one is if you have the difference between a convex function and a concave function, so h1 minus h2, that the difference is again convex. And this is just basically the same rule as the first one that I wrote down here. Because if this thing is concave, well, then negative h is convex, and the sum of h plus h1 plus negative h2 over here is also convex. Similarly, if you have a non-negative scalar, and you multiply that by a convex function, the result is again convex. Or you do the same thing with a concave function. Okay, nothing has changed. You maintain the same curvature. So like if you have x squared or 5x squared, nothing has really changed with curvature. Of course, if you multiply by a negative scalar, so if you go from x squared to negative x squared, then this is no longer true.
If you multiply by a negative scale, will become concave.
Yes. Yeah, so if you take a convex function, multiply by a negative scalar, it will become concave. Okay, and then let's see. If we have a bunch of convex functions and a bunch of non-negative scalars, if we take the weighted sum of a bunch of convex functions, that whole weighted sum, weighted by all these non-negative weights, is again convex. And then the maximum of a bunch of convex functions. So that max is also a convex. Yeah. So this thing basically says you evaluate the function value. So first of all, take an x of your choice, plug it into each of the hi functions, and then you get back a bunch of numbers, 12, negative 27, 83, whatever. And then basically says pick the largest number that's returned by any of the functions. And that's what the max here outputs. So one interesting example of this last rule is what are called piecewise linear functions. So imagine a bunch of lines, and then you take the maximum of all the lines, basically. So that thing will be bowl-shaped. It will be a convex function. Getting good notes for like drawings that I can make in the slides for next year. Okay. There are also composition rules for monotonicity that end up being pretty useful when you're trying to sort of build complicated convex functions out of simple sort of atomic functions. So if we have two functions, g and h, that are both scalar valued functions of scalars, and take f to be the composition, g of h of x, we get a bunch of different cases, basically 4 cases, depending on the monotonicity of the inner functions, g and h. So if they're both, g and h are both non-decreasing, then f is again non-decreasing, and everything is cool. If g and h are both non-increasing, then f is again non-decreasing. You can see this. So because h is non-increasing, remember a non-increasing function is going to flip the direction of the inequality. So this says if x is smaller than y, then h will be bigger than, h of x will be bigger than h of y. And then for g, again, non-increasing, so we flip the direction of the inequality again, and then we get that g of h of x is going to be less than g of h of y. So we had one flip from sort of a non-increasingness of one function and another flip from the other one. 2 flips gets you back to the original monotonicity. Okay. And then the last 2 cases you can guess are going to be non-increasing because they're each going to involve sort of one flip of the direction of the inequality. So if you have one non-increasing, one non-decreasing, the result is non-increasing. And the order in which you do the composition actually doesn't matter. Okay, so that's all for composition rules. Any questions about this before we just show some pictures of convex and concave functions? Yes.
If like the function is constant, is it both non-increasing and non-decreasing at the same time?
Oh, so the question is, what about a constant? Is a constant, what are its monotonicity properties? So if you just imagine the line, so think about R2, a two-dimensional space, the plane, and the line y equal 1. Right? So that line is non-increasing. It's not going up. It's also non-decreasing. It's not going down. So it is both. Yes. And then the curvature property. So is it convex, concave, affine? Like what would a line be? Sorry, a horizontal line be? Yeah, a constant function is a very simple example of an affine function, right? So because a constant function is affine, that tells you that it's both convex and concave. Yeah, you're right. And yeah, it's not, yeah. Okay, so that's the composition rules, and these are the rules basically that that are implemented in the software tools that we're going to use to verify basically convexity of functions. So the way that CVX and MATLAB works, for example, is you give it a problem statement and you build that problem out of a bunch of sort of atomic functions that are known to the CVX toolbox. And then you combine them in whatever weird ways you want to do, looping over time steps in a dynamical system model, for example. And then CVX has these rules that says, okay, for every transformation that you do, I'm going to check what did that do to the curvature and to the monotonicity of the function. And the atomic functions have these tags. They have a curvature tag and a monotonicity tag. And it just does the accounting. It just applies the rules that we just showed. And it verifies basically each step along the way that what you have done, the set of transformations that you have done are sort of legal within the rule set of convex optimization. And so if that is true, then CVX will go and give your problem to a numerical solver. It will get the right answer, a globally optimal solution, and it will give it back to you. But if at any step along the way, it detects that you've done something that does not follow sort of the rules that we just outlined, then it will give you an error. And it will say your problem is not certifiably convex. It might be convex, but it didn't follow the sort of limited set of composition rules that CVX uses. And so it'll say, you might want to respecify your problem, and it might tell you where the error is and give you some suggestions for how to fix it. But then that procedure of how to do the fixes, how to sort of correct your modeling and your coding, that again is really where the art and the craft of convex optimization comes in. And that basically boils down to being able to recognize curvature and monotonicity and understand how these things change in compositions of functions. So that's like why we did what we did. And next lecture, again, after spring break, by the time you guys have forgotten all of this, we will start with basically looking at how the convex optimization software works. Okay, so let's look at some of those atomic functions, the building blocks that we use for building up kind of interesting and complex convex functions. So one example is the absolute value. Let me move this a little bit here. So this is, let's see, what are the curvature and monotonicity properties of absolute value? So how about curvature? Is it convex, concave, neither? Convex, right? Yeah. So look at the stuff that's above the graph here, draw a line between any 2 points, all good. That's a convex set. And no monotonicity property, right? So I guess over here it's increasing, over here it's decreasing, but we can't say anything about it over the whole domain of all the real numbers. All right, so what about the function? This is called the positive part function. So basically you take x and you say, I only care about the parts of x that are positive. If x is negative, I'm going to give you 0. So curvature here, convex, monotonicity, non-decreasing. Yeah, which is cool. That tells us that like if we plug any convex function into this function, max of 0 and x, so stick any convex function in here, max of 0 and x to the 47th power, you get back a convex. Cool. X squared, convex, no monotonicity properties, right? Other polynomials with positive and even value here are also kind of, they follow the same curvature and monotonicity properties. They just get kind of increasingly steep as you go above the point x equal 1 and less steep, I guess, below. So here's x to the second, fourth, and sixth, all good, all convex functions. Actually, I think I made a mistake. I think I said over here, if you plugged x to the 47th power in here, that you would get a convex function. And I think that's wrong because x to the 47th power is only convex for positive arguments, and it's actually concave for negative x. So easy to.
Zero.
Oh, but yeah, it's zeroing out, right? So if we said the domain that we care about is only sort of the positive x's, then I think we're all good here.
But even a negative x, the max with a, if it's like -1, it'd be 0 or -1, so 0 would be max, so it's remaining. So you can keep the whole thing.
I don't know. Plot the max of 0 and x to the 47th power from -1 to 1 and see if it is bowl-shaped. I actually don't know. This would be maybe, should we do it? Let's see, I think there's a Mac app called Grapher. Someone has a graphing calculator. All right, great, go. Maybe not 47. How about max of 0 and x to the third power? Okay, yeah, I guess all good. Still convex. Although I think that if you programmed it in CVX, it might give you an error. It might say, oh, I don't know, like that's not following any rule that I know of from the composition toolkit. I don't know, we could try it. Yeah, it's a weird function to force, but sometimes in applications you end up wanting to optimize a weird function. That's okay. All right, so here's our positive value here. So these are convex. Here we get another set of functions if we restrict the domain of the function to being only positive arguments. And we take x to the power p. And we have power greater than 1. So we're not looking at square roots, for example, which would be concave. We're looking at power greater than 1 here. So this thing is, let's see, curvature is convex and monotonicity is non-decreasing, right?
Couldn't we go farther and say it's increasing?
It is strictly increasing, yes. We could go further. Okay, what about the sort of square root case? So if we again restrict only to the non-negative x, and we look at the same power function x to the p, but now we use a power p that is between 0 and 1. Here's what a few examples of that look like. So curvature here is concave, monotonicity is non-decreasing. Okay, another power example, restricting to strictly positive x this time, and taking the power to be negative. So this is sort of the 1 over x and functions that look kind of like that. So here's 1 over square root of x, 1 over x, and so on. So curvature, convex, yes, and monotonicity is what? Non-increasing. Okay, exponentials. So e to the alpha x, x any real number, and alpha non-negative. A couple examples of that. Curvature, convex, monotonicity, non-decreasing. So again, like if you take a convex function, any convex function, and plug it into an exponential, the result that you get is going to be convex again. Okay, exponential function with a scalar in the exponent that is not negative. What if the exponent scalar here is negative? So in this case, here's a few examples. Curvature, convex again, monotonicity is non-increasing, right? So we flipped from the last slide to this slide, we flipped the monotonicity property when we multiplied by a negative thing, but we maintained the curvature. Okay, the inverse of an exponential, a log. So let's think, I think, again, for the log to be well-defined, we need the argument to be positive, at least if we're dealing with real numbers. So let's do that and take alpha to be positive as well. A few examples of what that looks like. So here, curvature concave, and monotonicity decreasing. Okay. And this is, Zach, to your question of what this max function looks like. This is an illustration of it, just in the, I guess, R3. So here we have x1 and x2. This is a three-dimensional plot. So this is basically a plane over here, and it's a different plane over here. And basically, if you want to evaluate what the max of these two planes would be, you would evaluate each of them and then pick the bigger value. So what's the curvature of this guy? Convex. Who thinks convex? Who thinks anything but convex? Okay. Yeah, it's a convex function. And what about monotonicity here? Yeah, it's a little hard actually to specify that. So non-decreasing in x1, also non-decreasing in x2, right? So if we fixed a value of x1 and looked at this thing only as a function of x2, it would look kind of like, I guess, an absolute value sort of thing. It would have kind of a kink in it. But that's fine. That's a convex function, even though it's not smooth or differentiable. Okay, so this is convex, and we would call it element-wise non-decreasing. So non-decreasing in each of the arguments, x1, x2. What about the min? So this is kind of the opposite of that. So curvature, concave, yeah. So right, if we pick 2 points and we draw the line between them, that's going to be below the function. So that tells us this thing is concave. And then what about monotonicity? Non-decreasing, yes, in both x1 and x2. Okay, and we're almost done here. So the last kind of class of functions that I think are that come up pretty regularly in lots of different applications are what are called norms. So I'm sure in a vector calculus or a linear algebra class, probably you talked about norms, but we'll just go through them again. So a norm is a function that gives back a scalar, in fact, always a non-negative scalar, and it can take arguments that are vectors. Actually, there are matrix norms as well that would take a kind of an m by n input, but we'll just talk about the vector norms. So a function is a norm if it satisfies 4 properties. And so one is that it's always non-negative. Another, I think this is called homogeneity. So this is non-negativity, homogeneity. This means basically if you get a 0 value of the norm. So this inequality here holds with equality if and only if the argument is the origin, is the vector 0 in Rn. Okay. This thing is called something that I forget. But if you multiply by any scalar, so if you stretch or contract the vector x, basically, that the norm is just the absolute value of the factor by which you stretched or compressed the vector times the norm of the vector. And that holds for any x and any alpha. And the 4th property here is, I guess this is the triangle inequality. So this says if you take the norm of the sum of 2 vectors, x and y, that is no larger than the norm of x plus the norm of y. And that holds for any x and y. So if you think about what these things mean, you basically get that a norm is essentially a measure of length, the length of a vector. Right? So this says a vector has 0 length if and only if it's sort of a point. It's just sitting at the origin. Right? And for any other vector, it's pointing in whatever direction. It can be pointing positive or negative. Wherever you go, it has some non-zero length, and in fact, some positive length. And then this one says basically if you stretch or contract that vector, that the length of the stretched out thing is just equal to the scalar, or the magnitude of the scalar times the length of the original vector. And then this one, again, like I guess I could go back like 10 slides or 30 slides and show you the illustration of kind of vector addition, right? X and x plus y and so on. But this basically says that if you add 2 vectors kind of tail to tip, that the length from the start of the first vector to the end of the second vector, that length is never going to be longer than the sum of the lengths of the 2 vectors. And you'd get that only if you added them kind of if they were exactly perpendicular, or exactly parallel, right? Yes.
I
Yeah.
didn't learn norms.
Okay.
So how do you compute the norm?
Yeah, so how do you compute the norm? So this actually doesn't tell you what is like how do you get the norm? Like if I give you a vector, how will you tell me what its norm is? And actually that depends, and there are many definitions of norms, and we'll give three common ones, but actually there are many other ones. So just a sec for that. So all norms, yeah, that you can be viewed basically as a generalization of the absolute value. So that basically the size of a number, a real number, whether it's -12 or 47, you can take the absolute value of that number and it gives you kind of an idea of the length from the origin to that point. And they provide measures of length or measures of distance. So the norm of a difference, x minus y, you can interpret as the distance between x and y. So you can imagine why this comes up and why norms come up in a lot of applications. So for example, suppose we were trying to predict something and it was a vector thing. And we have two things. We have the true thing that we're trying to hit, the target, and then we have our own prediction that we made. So you might want to minimize the distance between those two things. Your prediction is in some sense better the closer the vectors are together. But the notion of closeness kind of depends. It's unambiguous in kind of the scalar case, but when you're out in a weird high-dimensional space, it's a little bit harder to pin down exactly what you mean by the distance between two things. Norms are always convex. They don't have a monotonicity property in general. Okay, so here are some examples, Grant, to your question of how would we compute the norm. So a simple one is what's called the taxicab or the L1 norm. And so this basically says the norm of x, the one norm or the L1 norm of x, is just the sum of the absolute values of x. Another, and this is kind of the default norm that people typically use. So if you just type in norm of some vector in MATLAB, it will give you back the 2 norm, the L2 norm. This is also called the Euclidean norm. Going back to Euclid, defining a lot of the notions that we use in geometry. So what we think of in three-dimensional space as the distance between 2 points, that is the Euclidean norm between the vectors that point to those 2 points from the origin. So here, this is the square root of the sum of the squares of the components of x. So although you may not have talked about norms, Grant, in your multivariable calculus class, you probably talked about the distance between things, and it would have been this same formula. And then there's something called the Chebyshev. This is a name, a Russian mathematician genius who we talked about, I think, last lecture when we talked about Chebyshev approximation as a way to do data fitting. The Chebyshev norm, also called the L infinity norm, is defined as the maximum of the absolute values of the components of x. So just like in the L1 norm, we would compute all the absolute values, say how big are all the elements of the vector. But then rather than adding them up, the L infinity norm would just take the maximum, take the biggest. And so let's look at what the kind of notions of distance would be. So imagine we have a point x, and I guess for concreteness, imagine that we're looking down at a map, say of a city. And this is, I don't know, your house or something. And you're using a map app to tell you how far you are from some point. Maybe you want to walk there or drive there, you want to plan your trip, right? So the one norm is a little bit weird. So the L2 norm would just be like, look at the vector here that points directly to x and look at what you would imagine is kind of the length of that vector. The L1 norm, actually, it's called the taxicab norm because it's kind of like has this right angle notion of distance, right? So it would be like first drive west this far and then drive north this far. And so add up the west distance and the north distance and you get the total distance. So taxicab is like if you were a cab driver in Manhattan and you were driving business people around between skyscrapers or something like that, this is the distance you would actually have to drive in the city. The 2 norm then would be kind of like the as the crow flies distance, right? So this would be if you had a helicopter and you could take off from one skyscraper and this analogy is getting very tortured, I don't know, and fly to the roof of the next skyscraper. That would be roughly the distance that your helicopter would cover. And then, so this is kind of the natural one that we think of as a notion of distance. This one I think is pretty easily comprehensible if you think about city grids, basically. And then the Chebyshev norm is like a totally weird notion of distance, but it basically says, well, how far west did you have to drive? And you say 10 miles. Well, how far north did you have to drive? Well, 7 miles. And it says, okay, the distance is 10 miles. You're like, but what about the north? It's like, don't care. All I care about is the bigger of the west distance and the north distance. Yes.
So do we only use the choice type whenever we're dealing with, I guess, scenarios in which that makes sense? So like, whenever one is massively larger than the other, is it a simplifying?
Oh, that's interesting. Yeah. So the question is like, when would we use the Chebyshev norm, and would we use it in the case where like one distance is way larger, one component of a vector is like way larger than another? Actually, it's an interesting point. Like there's a limit. Like if this thing was super duper far west and only a tiny bit north, then the Chebyshev norm would pretty much agree with the Euclidean norm and the L1 of the taxi cab norm, right? So yeah. Yeah. And if you got infinitely far in the west axis, right, then yeah, they would all be exact in that way.
More conservative. Last class, so this is more aggressive.
Right. So we saw that like in the data fitting example, that the Chebyshev approximation was in some sense more conservative. It was like, oh, I want to be really close even to the outliers. And so it was sort of pessimistic in that sense. And here it's kind of optimistic. It tells you, oh, the distance is only 10 miles, even though you have to drive 10 and then 7, right? So yeah, I think the notion of whether you're looking at sort of, it always goes to extremes, right? So it's either looking at a best case or a worst case, I guess. And the notion of whether it's optimistic or pessimistic sort of depends, I guess, on the usage. Does that make sense?
Pessimistic.
Yes, it's super pessimistic for the taxi cab driver, right? If you were an Uber driver and you only got paid for the Chebyshev distance that you drove people, you'd probably be a little bit mad about it. Right? Shouldn't give Silicon Valley billionaires any ideas. Okay. Any questions about the content from today? Great. Okay. Well, have a good spring break, and we'll see you in about 2 weeks.